All right, kiddos, hope you're doing well. Good job today using that Geometry Sketch pad to create that little circle sheet. So what I want to do right now is to show you two types of problems. They're a little bit complicated that use either radius perpendicular tangent or the two-tangent theorem. So the first type of problem is called a common external tangent problem. And so what we have here is we have kind of two circles, and this guy right here is a common tangent, meaning it glances off at one and only one point each circle. Um, and so a common external tangent is called external because it's basically on top as opposed to kind of slicing between them. This guy right here could be a common internal tangent, right? But this guy right here, just so you know, is called a common external tangent. It's tangent to both circles. And so what we have here is an opportunity to kind of consider this type of problem, where if we know the radius for both particular circles and we know how far apart they are, we can actually evaluate the length of that common external tangent. So here's what we're going to do. I'm going to first start by creating a radius to the tangent. And remember that the radius interacts with that tangent in what way? That's correct, perpendicular, right? So remember, radius is perpendicular to tangent, so those are right angles. Might not look right angles, but I drew it and sketched it up quickly. Okay, but those are indeed right angles. Okay, because remember, the radius of a circle is perpendicular to tangent. Right? So I first create that opportunity. Now I know the lengths of both of these radii. I know that's 6. So I'll put a 6 there, and I know that's 3. Okay, just to keep myself ready to go. All right, the next thing I want to do is create what's called the center to center distance. So I'm going to create the segment from the center of one to the center of the other circle. Right? And that has a length, and I can find that length because it's the first radius, 6, plus the distance between, which is 4, plus the other radius. Right? So I basically add the radius here, which is 6, to the distance apart, which is 4, and then the last piece is the radius, 3. Right? Remember, all radii of the same circle are congruent, so if that's 3, then that has to be 3. If that radius is 6, that radius is 6, right? And then that little piece in between is 4, right? So regardless, the whole, therefore, center-to-center distance is 6 plus 4 plus 3, which is 13, exactly, right? So I'm going to put a 13 somewhere around here. And the 6 and the 4 and the 3, of course, make up that 13, right? So now what I want to do is I want to kind of create an opportunity where I can potentially use the Pythagorean theorem. So what I do is this is a trapezoid, right here, my parallel sides. And what I want to do is I want to create from that trapezoid a rectangle on top and, more importantly, a right triangle on bottom. Okay? So really what I'm going to use to solve this problem is this right triangle that I created from this diagram, right? So I know that this piece right here is 13. It's the side across from the 90. It's the hypotenuse. I'm looking for this piece right here, which is the same as the length of the common external tangent. That's a rectangle, right? So those two pieces, those two lengths are the same. So I guess that question mark here is the same as that length of that opposite side of the rectangle that I created there, right? So now I just need this piece of the right triangle. It's not 6. Remember, the whole radius is 6. This piece up here is 3, exactly, right? Because it's a rectangle. 3, 3, right? 3, 3. Question mark, question mark. So if the whole radius is 6 and the top part is 3, what's the remaining piece here? That's right, 3. So you subtract. So therefore, this piece right here is going to be 3. Okay? And so now what I'm going to do is I'm really just going to focus on that right triangle here in the bottom and use the Pythagorean theorem, right? So the Pythagorean theorem would say 3 squared, 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 where's the square? Oh, there we go, 3 squared, plus, this is the other piece which I'm trying to solve for, really, these two are the same, right? Plus whatever, we'll call it x or question mark squared, call it question mark squared. Oops. Equals, by the Pythagorean theorem, the hypotenuse squared. Now the hypotenuse is 13 squared. Keep doing the same thing. 13 squared, right? That's by the Pythagorean theorem, right? So based on this right triangle here that I created, I can solve for that hypotenuse, excuse me, not the hypotenuse, the leg, by using Pythagorean theorem, right? And this leg here is the same as the length of the common external tangent, because that's a rectangle. Those two are the same. All right, so now I just solve for the question mark, right? So question mark squared is 169, which is 13 squared minus 9. So question mark equals, that's kind of annoying with that question mark, but we'll keep it as question mark. We'll continue to go there. So whatever we're looking for squared is equal to, if we're to do this out, that's 169, and that's 9. So when you subtract, you get 160. Right? And now when I, take the square root of both sides, I get the piece I'm looking for is the square root of, that's right, 160. Really plus or minus next year in algebra land, but it's a positive length, so it's just going to be positive for us. So now I just need to clean it up. 160 is indeed, was it 4 times 4? 16 times 10, right? The square root of 16 is 4, so out comes a 4, and in stays the 10, right? Okay? So this piece right here, which I solved for using the Pythagorean theorem, is the same as the common external tangent, what I'm looking for, which I just found is 4 root 10. Cool, huh? Okay, so that's a complicated process. We'll go over a couple of those tomorrow. All right. The second type of problem, this uses the idea that we discussed today called two-tangent theorem. And remember that the two-tangent theorem says that two tangents from the same external point to the same circle are equal, right? So those two are equal. These two are equal. These two are equal. And then these two are equal, right? So what we have here is we have a situation where we have a circle that's inscribed. It's within a quadrilateral, which makes essentially the quadrilateral consists of tangents, right, to the circle on the outside. So here's what we can do. This is called the walk-around problem, and one way to do it is using the two-tangent theorem. So what I'm going to do is I'm going to start with this whole side. I'm looking for this whole side. I know that's 7, that's 10, that's 9. And so I'm going to call part of that x. I'm going to call this piece up here x. Right? Now what I'm going to do is I'm going to walk around the whole diagram until I get back here, and then you'll see what we're going to be able to do. Right? So if this piece is x, what's that piece? That's right, x. They're the same by the two-tangent theorem. Right? So by the two-tangent theorem, that piece right there is equal or congruent to that piece. Right? Now if the whole side was originally 7, and this piece is called x, what's this piece left called? That's right, 7 the whole minus x. Very good. Okay. So that piece is called 7 minus x, which is wonderful. Because if this piece right here is 7 minus x, then what's that? That's right, 7 minus x. By the two tangents theorem. Okay. And so what we're going to do is we're going to continue to walk around in the same manner and name each particular piece. Now, here's where it gets a little tricky. If the whole side is 10, and part of that side, which is a tangent, is 7 minus x, what's this piece called? Now here's where it gets a little tricky. It's the whole, which is 10, I'll write it off to the side, minus the quantity, the piece that I know, 7 minus x. Right? So it's the whole, which is 10, the whole length is 10, minus the part that I know. Now what's tricky is you have to put the part that you know in parentheses, right? So what happens is the negative sign distributes 10 minus 7 plus x, right? The negative sign distributes. So it ends up being really 10 minus 7, which is 3, plus x. Okay, so that's a name for this piece right here, right? So that is the same as that when you distribute the negative sign. Okay. Now, by, again, the two-tangent theorem, these two guys are the same. So if that piece is 3 plus x, this piece also is 3 plus x. 3, plus x. And once again, if I know the whole side of the quadrilateral is 9, and I know part of the side is 3 plus x, then the other part is the whole, 9, and I'll write it off to the side, minus the quantity, the part that I know, the quantity 3 plus x. All right, and again, when I distribute, it cleans up kind of nicely. You get 9 minus 3, which is 6, minus x, right? So this piece really is 6, 9 minus 3, minus x, right? And again, these two are equivalent, right? I just distribute the negative sign. 9 minus 3 gives you our 6, minus x, right? And so again, if that tangent here is 6 minus x, then that tangent here is 6 minus x by the two-tangent theorem. So really what we have now is we have the two pieces of the whole segment that I'm trying to evaluate, right? And I know part of it's x, and the other is 6 minus x. So to find the whole length, I just add these two together, right? And then what's x plus 6 minus x? That's right, 6. Okay. So we just work our way around using the two-tangent theorem. Those are equal. Again, using the two-tangent theorem, those are equal. Two-tangent theorem, these are equal, etc., etc. And we work our way around, starting with part of the side we're looking for, all the way around. And then we just add these two pieces together to get the whole. And if we're doing it right, the x's will cancel one another out. Okay? So there's a walk-around problem. The first problem is called an external common tangent problem. They're both pretty tricky, and we'll go through most of those again tomorrow. Have a great day. Take some good notes, and we'll see you tomorrow.